Hi everyone, this is Umakan. Welcome to all of my channel. So here I am with a new video. So in this video I will discuss all about AFM and STM. So as you know, this AFM is a atomic force microscopy. This is atomic force microscopy. So this is a required tool in order to have the information about the surface roughness of a thin film of any sample. So let's have a discussion and have a great details on this tool. So basically SPM stand for the scanning probe microscopy. This SPM is stand for the scanning probe microscopy. And if you see then SPM from SPM, we'll get the information like surface information basically is there. So it includes surface roughness, which is most important, and height of the structure. Suppose you have grown nanotubes or nano wires or nano flowers on the surface of a substrate. So height of the structure, that is height of this nanotube or nano wire, and the width and the length of this nano flowers, you can estimate this height of this structure by doing this SPM. Then the 3D image of the surface you can get from this SPM. So this SPM is basically consist of two things. One is STM, that is scanning tunneling microscopy. So we'll have a great details on this topic. And the second is AFM, atomic force microscopy. So this AFM is consist of two things. One is STM and second is AFM. So this STM is scanning tunneling microscopy. So this STM is done for the conducting material. This is important. This STM is always done for the conducting metals or conducting elements. So why this is so, I'll describe in the next slide. Then this AFM is stand for atomic force microscopy, and this is for the non-conducting material. So now you are clear that both the tools of STM and AFM are there in order to have the surface roughness, height of the structure, and 3D image of the surface. So this is the three basic characteristic or the basic information that you can draw from the STM and AFM. Okay, so these two tools are collectively known as SPM. Okay, so move to the next slide and have a discussion on the STM. So this slide is looking very beautiful, and it is also important in order to have the great information is hidden in this slide. So we'll deal with the each figure one by one. So what is this STM? So basically one thing I would like to suggest to that, this STM is, the mechanism behind STM is very simple. If you know quantum mechanical tunneling, okay, then you can understand what is STM. So what happens is like, there is a piezoelectric tube with electrodes, and there is a metal tip is there. So there is a metal tip. This is the metal tip, okay, and this is the surface of the material. Okay, this is the surface of the material. There is a roughness, you can see there the surface roughness is there because irregularity is there. So whenever, and this material is conducting, this is important, the sample is conducting. Why this is so, and what is the need of this conducting substrate? Because whenever this tip is coming to the close to the surface, okay, suppose this tip is coming to this portion of this surface, then depending upon the gap between this metal tip and this surface, okay, there is a quantum tunneling of the electron from the metal to the metal tip, or the surface of the sample to the metal tip, depending upon the biasing, okay, what kind of biasing you are providing. So this tunneling of electron from the metal surface or the material surface to the metal tips depend upon the distance between this metal tip and this surface of the material. Okay, so that's why I am mentioning a point, tunneling current. This tunneling of electron will create to the will lead to the generation of the tunneling current. That's why the tunneling current is equal to the function of distance between tip and sample surface. This is very vital point. Okay, so this tunneling current is a function of distance between this tip and the sample surface. Suppose the tip is here, okay, so now distance is very small, so current will be small. Suppose this tip will come to this portion, okay, so see, now the distance between the tip and the sample surface is more because there is a dip in the surface. Okay, so this lead to the more current, more tunneling current. So the tunneling current will indicate that how much separation is there between the metal tip and the surface of the sample. Okay, that is the straightforward point. and depending upon the tunneling current you can estimate the surface roughness, because the tunneling current will lead to the surface signals and the signals can interpret as the surface roughness image. Okay, so this is simple, this is very simple, because if you see to illustrate in a great details, then suppose this is the surface roughness, sample surface. Okay, now your tip is moving in this height, this tip is moving in this height. Suppose your tip is now here, so now the tip is here, so the distance between the material surface and the tip is like d1. Okay, so now your tip is coming to this point, your tip is coming to this point. So now the distance between your tip, metal tip and the sample surface is d2. Okay, so it is clearly observable that d2 is greater than d1. So tunneling current for this d2, let I2, this is the tunneling current I2, will be less than I1. This tunneling current will indicate that how much separation is there between the metal tip and the sample surface. So this difference or this change of the current will lead to the a signal which will act as the surface roughness of the material. This is simple thing. Okay, so that is all about STM. Why conducting surface is taken? Because conducting surface will lead to the generation of the electron, and this electron can easily tunnel through this air barrier, because there is air in between this metal tip and the sample surface, and this air will act like an insulator, or you can say a barrier for the electron tunneling. Okay, so electron whether tunnel from the metal tip to the surface or the surface of the sample to the metal tip, it will depend upon the biasing you provide. Okay, if we change the direction of the biasing, now current direction will be changed. That does not matter for the information, but the thing is the current, that is the tunneling current, must change, because as per the surface roughness, if there is no roughness, the constant current will start flowing. Okay, so roughness will be 0, and the unit of the roughness is always nanometer. Okay, so move to the AFM, and like STM, AFM is working like in similar way, but the thing is like there is a conducting surface is needed for STM, and for the AFM there is non-conducting surface. Okay, so come to the AFM. The AFM is very simple to understand. First of all, for the AFM you don't need any conducting surface, you should have the non-conducting surface. Why? I will tell. And no need to quantum tunneling between the of the electron between the metal tip and the surface of the material. Okay, there is no quantum tunneling, but in between the metal tip and the surface of the sample, the molecular interaction is there. This molecular interaction maybe have the van der Waals interaction or the any kind of electrostatic interaction. Okay, so in STM there was a quantum tunneling of the electron between the metal tip and the surface of the sample, but here due to the molecular interaction between this metal tip and the surface of the sample, because on the surface of the sample there are lot of molecules or the atoms, and the metal tips also contain a lot of atoms, so there is a molecular interaction between the van der Waals interaction or the electrostatic interaction between them. So depending upon the strength of interaction, okay, strength of interaction, this cantilever will start moving. Okay, so in order to have a great simple details, I would like to suggest you in a way that suppose this is the surface of the sample. Okay, this is the sample surface having roughness because there is a zigzag manner of surface. Now your cantilever is here. Suppose this is your cantilever, tip is there. Okay, so cantilever tip is here and your sample surface is here. So the molecular interaction distance is like d1. Okay, because you know the closer, the more closer the tip to the surface is, more molecular interaction will be there. If molecular interaction will be there, the attractive force will be there, and this cantilever will start moving downward direction. If cantilever will move in a downward direction due to the more van der Waals interaction between the surface and the metal tip, so this laser direction is fixed, this incident direction of laser is fixed, so this reflected direction will get changed because this is go down and your deflection direction will be in this way. Okay, suppose there is a less molecular interaction between the metal tip and the surface due to the large separation distance. Okay, suppose the distance of separation of the cantilever is here and the separation is more, so molecular interaction will be less due to the large height d2 or large separation d2, so molecular interaction will be lower. So molecular interaction is lower means lower attraction to the cantilever, so cantilever will fall very small. So this small downward motion of the cantilever will lead to the small deflection of the laser light. Okay, so in first case you are getting the reflected laser here because his photodetector is here which detect the number of photons coming towards it, Now the detector is here. Okay, so intensity will be different. Now you got why the different intensity of the reflected laser is less, because depending upon the distance of separation between the metal tip and the surface of the sample, the molecular interaction varies. If separation is close or small, the interaction is more, cantilever will more fall downward. Okay, so it will lead to the more deflection in the laser light. If separation is large, molecular interaction is small, so lower down motion of the cantilever is the small, so it leads to the small deflection of the laser. Okay, so this will reflected as the different intensities of the reflected laser light. This different intensity will act like a signal which signify the surface roughness of the material. That's it. This is all about the AFM. I hope you got the point. So if you see these are the examples of a different AFM image of the different materials. So if you see, then this is the AFM image for the graphene oxide GO. If you see, then this you can clearly observe the graphene sheets, because graphene oxide is a 2D material, so it has the graphene oxide sheets. So these are the graphene oxide sheets is there. So this is the AFM image. If you see these are the AFM image of the zinc oxide nanoparticles. And if you see this graph indicates the surface roughness. Okay, this unit of the roughness is nanometer. So how surface roughness is varying with the distance, micrometer. Okay, so if you move from the surface, that is from 0.5 micrometer to 1 micrometer, how your roughness is varying. Okay, so this is very important, because you may think why roughness is so important, because whenever you are working on the thin film technology for the device perspective, so you should have the minimum roughness, because this roughness will act like a trap, or it can seize the motion of the electron from one layer to the other layer wherever there is a heterojunction. So in order to have a great charge separation on the interface of between two semiconductor, metal semiconductor, or any kind of material. So suppose you are fabricating any heterojunction, one material and upon other. So if surface roughness is more in this interface, then electron or holes will get difficult to move from one side to other side. So you should have the minimum roughness. Okay, so now you may have the motivation why you are talking so much about the surface roughness and what is the importance of AFM. So that's why AFM is important, in order to get the information of the surface roughness, structures, height of the structures, and 3D image of the material or the structures. Okay, so thank you so much for your patience. Hope you got some important points from my video. Stay tuned with my channel. Thank you so much for your support. Thank you.